So let's start with the inverter. So I think everyone is familiar with the inverter right now. So this is your NMOS, this is your PMOS. That's your VDD, ground. V in, V out, right? What's the transfer VTC for this? So if I draw V out versus, so what I'm going to do is I'm just going to quickly go through it. So that way I'll have a recorded one, which is not like 5 hours long, and then we can discuss afterward. But if you have any questions, just stop me. If there's something quick, you should stop me. Okay. So I think everyone is familiar with the VTC curve now, right? So, right, something like that. I drew it very linearly, but it's not a lot non-linear than this. So if I choose the, so L we are going to take as L minimum. So we'll just take L minimum. That's what we do for inverters, but I'll show you that for amplifiers, that's not what you want. And let's say the PWP-WN ratio is the inverse of the mobility. So that way it's symmetric, right? So the transition point will happen at what? VDD over 2, right? So this is so when the input and the output are equal to VDD over 2, that's because it's symmetric, right? So that'll be one assumption. And we'll also assume that we have to consider lambda. Without that, it'll show infinite gain. So lambda n is equal to lambda p equals to lambda. Okay, so we choose some size and we get a perfect symmetric curve. And what we have been using the inverter is in this region, right? In this region here, these two regions, actually a little bit higher because that's your noise margin, right? Whatever is, yeah, depending on what the low value for the other one is, you roughly get that noise margin over here, or this is the noise margin, right? But now we are interested in finding, using it as an amplifier. So, when we did so now if I want to do dV out over dV in, how does it look for V in? It's basically almost 0, and then it goes up and then goes back on, right? And we choose this point. Actually, it's negative, so I should write mod for this. This is a negative curve, so I should write mod for this. So the places where it's 1, that's the noise margin points, right? The NML and NM high is where it's chosen. So for digital, we want to operate it here in these region, right? Those are your noise margin regions. Here you don't want to, right? Because once your gain goes high, you're amplifying noise. That's the reason you don't want to be. But now I want to use it as amplifier. Okay. So if I want to use it as amplifier, where should I use it? From in this curve, where do you think I should use it? I mean, which position in V in? Like if I want to bias it at a certain point in this curve, which is the ideal curve? What's that? Here, right? Right here, because that's where the maximum dV out over dV in, because I'm trying to use it as an amplifier, which means that dV out over dV in, I want this to be equal to whatever maximum I can get out of this device, because it's amplifier right now, right? Which is basically this point here, the transition point when V in equals to V out, right? So that's where I want to use the amplifier, because if I use it here, then if I give a small input, I get a large output. And that's my goal of using this as an amplifier, right? So before I do that, I need to see in digital, you don't need to bias it because you're giving extreme inputs. Your input is either a 0 or a VDD. But now I need to take this inverter and actually bias it right at that point. So just send and then give a small input so that the output is, changing as a function of the gain, right? So how do I bias it such that it actually, when I'm not giving the signal, when I'm in DC condition, it's actually sitting at this point? How do I bias it? What should I do to this circuit to do that? Hmm? Yeah, saturation, correct. So this is where both MP and MN are in saturation, right? So, but in the circuit, see in the circuit, if I just leave it that way, this can drift to any value. So typically it will not stay there. It will actually go rail to some value, because if there is a small noise at the input, it'll just rail it, right? So how do I make sure that at DC condition, when there is no signal, so let's say I'm doing it as an audio amplifier, or like I said, 2.5 gigahertz amplifier. So I have a LO signal, in the sense I have a sine wave coming in, I want to amplify that. So that's what typically it's used for. Actually, in your cell phones, the LO signal which is coming in, it's actually a bunch of these inverters biased at that point, and then you give a small signal and just keeps amplifying it. So how do I hold it there? Okay, so what is this point here? This point is when V in equals to V out. So how do I get V in equals to V out here? Just short it, right? If I just short it, I get V in equals to V out, right? But it's still not good for me, because if I short it, then how do I give a signal? Because all it's doing is doing VDD by 2. It's a nice bias for you. It's just a voltage divider for you. It'll do a VDD by 2 and give it to you, but it's not good for me to give a signal to it, right? So what do I do? So this is what I want. I want at DC, I want it as short, but once I give even a small AC signal, it should look like an open. What is a passive device which can do that? What passive device looks like a short at 0 frequency or DC frequency and is open at high frequency? Inductor, right? So I can just put an inductor here. Okay. And then for the signal, I don't want to mess up with the signal, because that signal has its own DC value. So I can't join it in DC, but once the AC signal is there, I want to pass it. What kind of passive element will allow me to do that? A capacitor, right? So if I take a capacitor, and if I take a capacitor here and put it in V in, that's it. That's my amplifier. Okay, so if I put a big capacitor and a big inductor, then what it will do is at DC, it'll come and just sit there, because the inductor will actually short the input and output. But once I put a small signal in, it'll allow to go through it, because it'll allow a LDI over dt, right? V equals to L. So there is a small current, there'll be a small voltage across it, right? So it'll allow this. But in IC design, we can get good capacitors. Even small capacitor is okay, because we're operating this at high frequencies, but inductor is impossible to get. Very high value inductor. Basically, one inductor will be the size of a chip, and that's what people use. They actually, you'll see like half of the chip is an inductor for RF amplifiers. But in this case, we can't use it. So in IC design, typically we don't put an inductor. What we do is, instead of putting a inductor, oops, we just put a huge resistor here. Okay, so we just put a big value resistor. So there will be a small current at DC just biasing this. But if my amplifier is such that there's a large amount of current flowing through it, then it is okay. So as long as the resistor is large enough, it is okay. And doing large resistors in IC design is not an issue. It's fairly easy to do it, as long as you're not expecting accurate values. And we don't require accurate values here. We just want something, large. Okay, so that's your amplifier, right? Okay, now let's analyze how much gain we get out of this, right? Um, so like as you guys said, um, it's in both the transistors are in saturation, right? At that point. So the idea is we're giving a very small signal to it. So we'll assume that both of them remain in saturation and then just find the gain. So the current through the NMOS transistor is what? Mu N Cox over 2 WN, L is the same, and VGS. And what is VGS for the NMOS? No, in VGS, the gate V in. And V in at DC is what? We are calculating all this in DC. At DC, what is V in? VDD by 2, right? So VDD by 2 minus VTN, right? And then here we have to take the channel length modulation into picture. Otherwise, you're going to get an infinite gain, because any small value of current will be infinite change in any small change in delta V, VGS will be a huge value in current. So you'll always get infinite gain. So we need to add the channel length modulation as well. And what is VDS? V out, right? So that's your NMOS current, right? What's your PMOS? P is equal to mu P C ox over 2, WP over L. And then what is V in? VDD minus VDD by 2 plus VTP. Yeah, you can do minus modulus of VTP, or let's keep the signs as it is for now. And then 1 plus lambda V out, VDD minus V out, right? That's your VDS. Sorry, square. Okay. So these are the two currents, and obviously they're equal because there's no other current flowing through. There is a current flowing through the resistor, right? There's a small current flowing through this bias resistor, but we neglect that because our assumption is that we have taken a huge resistor such that that current is much smaller compared to IDN and IDP. Okay, so we forget the resistor for now. Okay, so and we took all these conditions, right? L equals to L minimum lambda, and yeah, the other condition we're going to take is VTP equals to minus of VTN. So which, in other words, both the magnitude of both the threshold voltages are same, and in typical cases that's true, right? So if that's the case, then I can cancel this whole term, right? So IDN equals to IDP. If I take that equation, I can cancel this. This I can write it as V effective, right? So I'll call V effective, or you'll see people call it V on, or obviously know it as VD sat. They're all the same. So the VGS, this is equal to VGS minus VTN or VTP, and in our case it is VDD2 minus VTN, right? That's VDS. So this becomes V effective and V effective square. Okay. So if I now take both sides and equate it, I'm going to write it as V effective square, right? Plus, I'm sorry, 1 plus lambda V out is equal to, this is also V effective, right? Because VDD plus VTP, but we've sent VTP equals to minus VTN. So that's also V effective, right? So V effective square, sorry, times 1 plus lambda times VDD minus V out, right? Obviously, these two cancels out, but that's because they're DC, they cancel out. But now we're going to apply a small input to it, okay? So what we're going to do is we're going to add a small delta V in, which is a plus delta V in with respect to the ground. Okay, so basically your whatever the voltage is here, so it's basically the input now becomes VDD2 plus delta V in. Okay, so if that's the case, then because it's an inverter, the output will go minus some delta V out, right? So our job is to find out this minus delta V out over delta V in, and that will tell me what the gain is. Okay. So if I do that, then this is going to be V effective plus delta V in square, right? 1 plus lambda V out. Then because, see, now the currents have to be equal, right? So your square term has gone up. That means your output voltage has to go down to cancel it, right? Because the current has to be the same. So that means this will be minus lambda delta V out, right? And that's equal to, again, V effective, no, because it's a PMOS. So if the voltage is going up, delta VGS is going down, right? So basically, because this delta V is going up, this delta VGS for this guy, because it's VDD minus VG, right? So VDD minus, so if VG is going up, then delta V in is going down. So it's minus, right? So minus delta V in square, and then 1 plus lambda VDD minus V out plus lambda delta V out, right? Because now the current portion in your GM term or the square term is decreasing. To fight that, you have to increase your delta V out to go there. And that's happening here because when this voltage is going down, your VDS for the MP is going up, right? So that's the case. Okay, so everyone through this? Okay, so, and this is where now incremental analysis comes into picture, because obviously this is a nonlinear equation because I'm trying to find out delta V out versus delta V in, but the V in is encapsulated inside a square term. So when I expand this, I'm going to get a delta V in term, but also get a delta V square term. But then if I get a delta V square term, I can't, I can't find the linear gain, right? I'm trying to find if there is a linear gain for it. So just basically, I'm trying to linearize this equation here. So what I'm going to do is I'm going to write this a little bit different. So I'll write this as V effective times 1 plus delta V in by V effective, right? So then I'll have V effective square 1 plus delta V in V effective square, and then I'll have this term. And then what I'm going to do is yeah, actually, just to simplify this, let's do lambda V out here as well. It's going to be the same because V out is VDD over 2, right? We don't have to, sorry. I'm just going to, because V out is VDD over 2, right? So I'm just going to substitute that. So that way I don't have to carry this all over the place. Okay. So basically I substituted VDD minus V out, which is VDD by 2, and V out also, which is VDD by 2. So this is, and I'm just going to call this term some term K dash. So again, I don't have to carry this all over. So this is K dash, what is it? Minus lambda delta V out, right? Equals to V effective square 1 minus delta V in V effective square times K dash plus lambda delta V out, right? Okay. So you guys remember this? I'm going to go to the next slide and rewrite this. Okay, so V effective, these two I can cancel now, right? Okay, so I hope you guys remember now. So it's going to be 1 plus delta V in, V effective, right? Square, and this is what? K, did I say K dash or K? K dash plus minus lambda delta V out. Okay, and this is equal to 1 minus delta V in, V effective square times K dash plus lambda delta V out, right? Okay. So now I still don't have a linear equation, but what I'm going to do is I'm going to linearize this because my condition is that delta V in is so small that delta V in over V effective is much, much less than 1. If I do that and I do a Taylor series of this and neglect all the square, delta V square terms, then this becomes what? 1 plus 2 times delta V in by V effective, right? Times this term here is equal to, and this will be 1 minus 2 times delta V in over V effective and this term over here, right? Okay, so now let's simplify this. So I'm just going to write the whole thing just so that I don't make mistakes. So if I multiply these two, so I'm going to get what? K dash minus lambda delta V out plus 2 times K dash delta V in over V effective plus 2 times lambda delta V out times delta V in over V effective, and that's equal to, what is it? K dash again, right? K dash minus sorry, plus lambda delta V out minus 2k dash delta V in over V effective, and then minus 2 times lambda delta V in times delta V out over V effective. K dash.
Last term of LHS.
So did I make a mistake somewhere?
Last term of
Yeah,
LHS.
LHS side, the fourth term should be negative.
Yeah, I think it should cancel. This one, right?
Yes, sir.
Yeah, yeah. Yeah, so K dash will cancel. This negative term cancels out. Then if I keep all the V out on the left-hand side, then I get lambda times minus 2 lambda times delta V out is equal to, I push all the V into the right-hand side, then it becomes minus 4K dash times delta V in over V effective. Is that correct? Something doesn't make sense. Delta V out over delta V in should be a negative term. Mm. Oh, no, sorry. That's because I haven't shown the sign. Yeah, that's fine. Because I'm just doing the incremental. Um, maybe, did I miss somewhere? Okay, just check it. But I think the terms are fine. Just check the signs. So if I can now take delta V out over delta V in, that's equal to 2 times K dash over lambda times V effective, right? And this K dash is, I'm going to just substitute that K dash term right now. What was the K dash term? 1 plus lambda times VDD over 2, right? So I'll write it as 0.5 times lambda VDD, okay? Okay, so let's take a typical number. So that's, so you can see, you can get a lot of insight into this. So basically what we have done is this. We have, I mean, you guys are all familiar with this. You just, around this point, you found the slope. Okay, I just exaggerated it here. You found the slope and you said it's your gain. Obviously, that's only valid for a very small region of operation, because once you start going close to VD or ground, then it starts distorting. So that one is only valid for small delta V in, because that was what our condition was, that it is for small delta. So that's essentially what you have done. You've taken the entire gain equation and you linearized it about that point of bias, okay? And that gives you what's called the small signal gain. So this gives you insight into the gain of this amplifier. First thing you see is, what is the gain dependent on? It's dependent on 1 over lambda, right? So the gain is proportional to, and just do it another color. So the gain is proportional to 1 over lambda, and the gain is also proportional to 1 over V effective. This part here is actually a negligible term. I'll show you with some numbers right now. So it's basically this term here. And when we do the small signal now, after some time, we derive it using small signal. You'll see you'll get this same equation too. Okay, so let's take some numbers. So we're going to do 0.8 micron design, right? So 0.18, sorry, 0.18 micron design. So typical value for 0.18 lambda is about 0.08. So let's say zero point 0.1, okay? Sorry, lambda times L. So usually the foundry will give you a lambda times L number, okay? That's because the lambda depends on the L. The longer the length, the smaller the lambda, okay? So in other words, in terms of ID VDS curve, so you see how this slope, right? This is what your lambda is telling you. So if this slope is very high or very slow, that means your lambda is high. It's inversely reference to lambda, right? Because it's ID is equal to, if I write it here, ID equals to V effective square 1 plus lambda VDS, right? So if this quantity is small, that means you're varying. If this quantity is large, that means your variation is also large with respect to VDS. If this quantity is small, that means your variation with VDS is also small. And typically you want variation small because you want it to look like a current source, because that's ideally what it should look like, right? But that term is dependent on lambda. It's almost linearly dependent on lambda. This is a long channel approximation. Short channel is not, but you can approximate it as dependent on L. So typically the foundries will give you a lambda L term. So for example, in 0.18 is something like 0.05 or 0.08. So let's take 0.1. Right? So if your L is minimum, which is 0.18, then lambda is equal to 0.18 by zero point 0.1 by 0.18. I can get my calculator. Let me just grab my calculator real quick. You have a so what is zero point 0.1 by 0.18? 0.56, right? So times zero point 0.5 times, so for 0.18 VDD is equal to 1.8. So what is this number? 0.56 times 0.5, that's roughly 0.25 times 1.8 is what? Like 0.36 maybe, something like that? 0.5? No, can't be 0.5. Because 0.25 times 1.8 is, should be roughly 0.4 or 0.36. Can't be 0.534, right? 0.5, oh, sorry, yeah. No, can't be 0.54. 0.5 times 0.5 is 0.25. 0.2 times 1.8 is 0.36. Can't be 0.4, 0.54. Sanity check, guys. You remember, if your mother doesn't fit in super theory, it's wrong. Do that. So what is it? Okay, while you guys are doing it, let me grab my calculator.
It's 0.5.
0.504.
Yeah, you guys are right. So 0.5, that's because it's close to 2, and that's why. So this is roughly 0.5. So this number here, it's 1.5, right? 1.5. So your gain delta V out over delta V in is roughly 2 times 1.5 times lambda V effective. But like as I said, typically you take a large length. So your length would be, so when I'm doing this as an amplifier, I don't take it as a real minimum unless I want the highest speed out of it. So if your speed is not a concern, then you can take a longer length. So typically if you want higher gain, you take a longer length. So this term is actually almost close to 1. So your gain is actually 2 times lambda by VGS minus VT. And in this case, it is VDD by 2 minus VTN, which is VT because we said both the numbers are same. So it's inversely proportional to lambda, and lambda is proportional to inversely proportional to L. So you want higher gain, you do what? Higher length, okay? Or if you want higher gain, you do larger VDD, but you're stuck with VDD. Okay, so VDD is like in 0.18 is 1.8 volts. That's the highest you can go. So 0.9. And again, VT is also given to you, but you can use a low VT transistor to increase this gain. Okay, so those are your parameters you can control to get that gain out of it. Okay, there is another term which is not shown here, which is your current. How much current is going through it? You don't know. That's because that's not inside this. And that's where, because we assumed it is saturation, for whatever this VGS, you get that much amount of current. But I'm going to show you later in the slide how, you know, putting, instead of using saturation region, if you use the subthreshold region, then you're going to get the same amount of gain with a lot less current. If your speed is again not important. If you want the highest speed out of this technology, then you still go for saturation. If you're doing some kilohertz stuff and your transistors are way faster than that, then you can operate it in subthreshold, because what happens is for subthreshold, you make your transistor size huge. Sometimes they're like really big, which means that the CGS capacitor will be big. So whatever driving it is slows down. But if your signal is slow to begin with, yeah, just make it huge. If you don't care about the area that much, make it huge, and then your current required will be a lot less. So I'll show you a parameter, GM over ID, and I'll show you how they vary and how much current you can save going from saturation to um, subthreshold. Okay, so is this part clear now? Did I stop the recording? No. So it's clear. So basically what we did was we took an inverter and we said we want to use it as an amplifier. And in order to use it as an amplifier, we biased it right at the middle point by shorting the output input with a big resistor so that the DC is biased. But if I apply a small AC, it'll still give me a gain. The output will vary. And I wrote the equations for it. Obviously, the equations are nonlinear because the current equations are nonlinear. Then I linearized it about that bias point and found out this gain. Okay. So actually, let's plug in a number here and see what the gain is. So what did we say? Delta V out over delta V in is equal to 2 times, roughly 2 times lambda over V effective, which is 0.5 times VDD minus VTN, right? Or VT, let's say, whatever, both of them are same. So we said, so let's take L equals to 1 micron just for sake of for this problem. So we said lambda times L is 0.1, which means that 0.1 micrometer per volt. So which means lambda for 1 micron length would be 0.1 volt inverse. Okay, 1 over volt. So that's the unit for lambda, volt inverse. Okay, so that's the lambda. What else do we need? VDD, we said max we can go is 1.8. So 0.5 is this thing, and VTN. So let's make this 2 volts just to make the calculations simpler. And VT will take it is usually 0.45, something like that. To make our calculation easier, we'll make it 0.5. So this becomes 2. Lambda is 0.1. 0.5 times 1 minus 0.5. So that's 2 over, uh, what is it? 0.5 times 0.1 is 0.05, right? So 5 for 20, what is it? 40? 40, right? 40, gain of 40. That's really good gain for 2 transistors, right? So you get a gain of 40. So you give an input of 1 millivolt, you get 40 millivolt. You get 100 millivolt, you get 400 millivolt. You give 400 millivolt, you get what? How much? So
16,000 millivolt.
16,000 millivolt, which is 1.6 volt. And if I give 1 volt, then I get
40
40 volts.
volts.
Yes. Do you get 40 volts? Right. So, but even here, it's a problem because now we have gotten out of our assumption we made, right? Our assumption was it's very small. If you're very small, only it's linear. So by the time you get to 40 millivolts, it's not linear anymore. It'll start getting nonlinear. Okay. And obviously you won't get 40 volts because your supply is only 1.8 volts. Okay. So then it starts like an inverter. You give a 40 volt, it just goes rail, right? Still 1.8 volts. So yeah, don't make that mistake when somebody is trying to trap you like that. And also just remember, so now let me ask you this. So we said for a small delta V in, this whole analysis is valid. How small? How high can I go and still use this analysis? So this number here, 2 lambda by VDD, how high a delta V in can I go? How high? And still use this? VIH minus VOL. Okay, what else? Who can, people on the call, anyone can guess how much? before the noise margin. Okay. So it's an incomplete question actually, right? Because for no value of delta V in, it is valid because there is always that square term, right? So you have to ask me, what value of square term are you okay with, right? So every time even if I give a 1 millivolt output, it'll have, so I give a sine wave of, so square term in frequency domain means basically this. If I have a F in of 1 millivolt times sine omega t, what I'm going to get is 40 at the output, V out, I'm going to get 40 millivolt sine omega t, and I'm going to get some K dash sine 2 omega t plus K double dash sine 4 omega t. Actually, you'll get, this is single-ended, so you'll get the three terms too. So you'll get K double dash sine 3 omega t and so on. In other words, so let's say I give a 1 kilohertz signal, 1 millivolt, 1 kilohertz signal. You'll get a very close to 40. Actually, you won't get 40. Your power equivalent will be 40, very close to 40 millivolts, 1 kilohertz. You'll also get a 2 kilohertz signal. You'll also get a 3 kilohertz signal. You'll get a 4, 5, 6, and so on. But they'll be diminishing in their amplitude as the frequency goes higher and higher. Okay, so the question should be how much. So let's say I'm worried only about the second and the third harmonic. So 1 kilohertz, 2 kilohertz, and 3 kilohertz. Then the question should be, so if I did a frequency plot of the output, so this is F and this is the amplitude. So let's say V amp. So F in, so this is 1 kilohertz. I'm going to get 40 millivolts. Okay. Then I'm going to get 2K something. I don't know what it is. I don't know what the nonlinearity is. I haven't calculated it because I linearized it. Then I'm going to get 3K. Then I'm going to get a little bit higher, 4K, and so on, right? So asking me or asking you how much of a delta V is okay, your question should be, how much of this is okay for you? Tell me, and then I'll tell you what the delta V is okay. All the people who have prepared gate, including our HODs here, they'll say it's KT over Q. Okay, just take that argument, please throw it out. I don't know where it came from. It came from a BJT with some, but that's not true. Okay, I actually don't know why they say that. I mean, I don't know why people have written that gate, but that's why, probably tell you why that exam is a, bit of a nonsensical exam. So it's not KT over Q, right? Not bit of a, I don't have to be politically correct here. It's actually a very nonsensical exam. So it's not KT over Q, it's nothing. It all depends on how much nonlinearity I can handle. If you tell me I can handle only minus 30 dB or as high as 30 dB, then depending on the size, the nonlinearity of the transistor, delta V in of maybe 100 millivolt is fine, right? You plug in the values, see how much nonlinearity. If you say, no, this is too much because I'm doing an audio amplifier, it's a high fidelity audio amplifier. Then you say, okay, I want minus 90 dVc, all the harmonics, right? So this is basically in audio world, you hear a jarring sound, like your functions, like when the things happen, or the marriage processions, that's like a lot of F2s, second harmonics, basically. That's what it is, right? If you're hearing a sweet sound, there's no second harmonic. So if you want a sweet harmonic, then it's minus 120, 140 dBc. Then your delta V needs to be really, really small, 1 billion. And when we cover feedback towards the end of this analog lectures, you'll see actually you don't have to deliberately make that small. The feedback actually automatically does that. So you can take a nonlinear amp, put it in feedback, it automatically linearizes it, right? Like a simple op amp, right? If you just put it in feedback like this, what is your assumption? That these two voltages are always the same, which means the delta V in is 0. If the delta V in is 0, delta V in square is equal to 0. So obviously it's not exactly 0, but it's very, very tiny. And this tiny amount is because of the feedback. So the feedback actually takes a highly nonlinear system and makes it linear. If the output is nonlinear, if your input is heavily nonlinear, even for small input, then it can't do anything. But if your output is heavily nonlinear, then the feedback will actually correct it because it'll not allow it to become nonlinear. Okay, so that's what we've done. So the question is, okay, how high can I go? Well, the question back to the questioner or the interviewer is, okay, how high a nonlinearity can you tolerate? You tell me that, I'll tell you the delta VN. He might tell you, then you say, okay, I need to calculate, I need to go home and calculate, because it's not straightforward, right? You have to apply. Okay, it's clear, right? Everything. So I thought this will be a good segue from going from, so you've used the inverter as a digital, now you see how you can use it for analog, and now you know how to use, how you need to do biasing now, right? You just can't take things and do it, you need to bias them, because in analog, it's not like just sizing them, but the current also depends on how you bias them. Okay, in digital, you always just chose a size because your input was always a 0 or a VDD, and the size just took care of the transients, right? But here you're actually passing currents through them, so you need to bias them properly. Okay, so it kind of, I thought it kind of covers a lot of things and kind of gives you a nice sort of a segue transition into the analog world. Okay, so this is the crux of your incremental analysis or small signal analysis. Basically, you're taking a nonlinear system and you're saying, I'm going to expand all the Taylor series, drop everything out except the linear term, and just make sure that my input is valid for that assumption. In other words, when you're dropping the second harmonic, third harmonic, you're assuming the small, but it is small to the point where the second harmonic might be minus 100 dBc or minus 80 dBc, and you're saying that's negligible for me, that's why you're dropping it. If it is not, then you cannot apply the small signal analysis. Okay, so it's called clear. All right, any questions from the people on call? Everything is clear, or you have any questions? Okay, I'll take that as a yes. And so what I'll do now, I'll just kind of formally show you a little bit on how to, what is the incremental analysis. Take a diode example. Actually, this is example from one of the MIT's lectures. And I have a link, I think, to a YouTube video. You should see it. It's a very funny video in the sense. He shows how, well, actually, this one is not funny. The funny one is the noise margin one. The Anand Chand, edX founder, what's his name? Anant Agarwal, right? Anant Agarwal, yeah. Not Chandrakashan. This is Anant Agarwal. So Anant Agarwal lecture in the MIT one, both for the noise margin and this one is, it's actually quite nice. You should take, I have a link to the YouTube video on the slide. I'll show it to you. Okay. All right. So this is actually I'm not a big fan of this example, but it's still a good example to kind of sort of show you motivate behind how small signal analysis is used. So basically what he's showing here is you have LED, right? And you want to take like a music signal. So your music signal coming out of your cell phone, you want to transmit that through the light, and then there's a receiver, and it's usually a photodiode, and that receiver photodiode takes that light, converts it into current. So basically you convert the voltage of the music signal into the diode current, and that diode current is directly proportional with some loss factor to light. And then the photodiode takes that light, converts it back to current, almost again proportional with some gain factor, because there's also a quantum loss factor in that. And then that current, you use the TIA to transimpedance amplifier to amplify it, drive a speaker with a power amplifier, and then you get the audio transmission. So that's the sort of the thought experiment or experiment we are going to look at. The problem is this VI to ID, this is a nonlinear process. Okay, so sorry. So this process here is a nonlinear process. Okay, so you're giving a linear V over IT. Obviously, this is a music signal, but let's say you give one tone, like 1 kilohertz sine wave tone here. Then this ID which comes out, it's not, it's going to be distorted. Okay, and then obviously the light is proportional to ID, so that's also distorted. Then IR is also proportional to the light, and that also gets distorted. And the power amplifier is a linear power amplifier. It just takes a distorted signal, amplifies it, and you get that jarring kind of sound. And that YouTube video, when you watch it, you'll see he's doing a demo where he's showing all this. Okay, it's kind of a nice demo. So I did this, spent a lot of time doing this little animation. So not a lot of time, but so this is the ID-VD curve of the diode. Okay, so you're applying a voltage and this is your current through the diode. So if you apply the signal directly to it, so I'm showing a sine wave which is applied. So the sine wave is varying around 0 volts and there's a plus minus volt to it, right? So you're applying that. And so I'm showing this dot as the input is varying. I'm just basically tracing this, right? I'm just tracing from this point to here and I'm telling you that this is the current for this voltage here. And if the voltage is like VDD over 2, here it's a sine wave where it's pi by 4, then that's roughly here, which I trace it back here. That's this current. And I go to the next one at the peak, it's this current, and then, you know, back here and so on, right? So as you're going through the sine wave, that's the current you're getting, right? So you can see you're not getting a sine wave. You're getting this distorted signal. And that obviously is clear from the diode equation too, because you have Is to the power VD over T. And, you know, so basically this is a compressor, right? I mean, expander. So it takes small signal, expands it, and towards here, it just contracts it. So that's why you get the distortion. So what you do is if you look at this curve, you say, okay, if I use this entire thing, it's very nonlinear. But what I'm going to do is I'm going to use a very small portion of it. Okay. And that's very linear. And then once I receive the signal, I'll amplify it, right? Because the whole nonlinearity is happening from voltage to current conversion in the diode. So instead of giving a large variation in the voltage, I'll keep the variation small, right? And what's the easiest way to do that? So let's say you have this this thing. The easiest way is you just put a resistor to linearize it, right? So for example, let's say this was 1.8 volts and you know you're giving some 10 millivolt signal on top of it or 100 millivolt signal on top of it. Let's say I take a 1K resistor and let's say this is 0.8 volt on, then DC current is 1 milliamp, right? And then this 100 millivolt will be very linear because this 100 millivolt is 100 millivolt minus 0.8 by 1K. And if I assume that for this small current, the VD is not varying because it's exponential. So if you take the voltage, it's a log of that, right? So it's kind of compressed, right? So for delta V of variation, your delta V in diode is very small. So in other words, the current is almost linear. And if your current is almost linear, so what you have done is with this circuit is basically done this. You've biased it at some point here, which is in this case like 1 milliamp, and then you're applying a small voltage again, which is through this resistor. Okay, so that way it remains very linear. Okay, and we'll show with some calculations how why is it so linear. Okay, make sense? This is kind of showing you in a pictorial view. So basically you're taking a small linear portion. Obviously this also has the linearity, non-linearity in it. But like I said, if the non-linearity portion is small enough that, let's say in this case, the audio, if you cannot hear it, then it is fine, right? So for example, I cannot hear anything below minus 70 dBc or 80 dBc, or at least I can. So you keep giving it till it is minus 80 dBc, then I'm good, right? Before it was like maybe minus 10 dBc. So in other words, like how much ever signal I was giving, the distorted signal was like just 10 dB lower than that, which is very, very high, right? So that jarring sound you hear in all these marriage processions and all that is because of that harmonic. Okay, so so here is the process. So to linearize it, you take a nonlinear element. You first have to operate it at some DC biasing point, like we did for the amplifier just before. We operated at VD over 2, right? So you operate it at some point. So in this case, the diode, we operated at some value VD. And then you superimpose a small signal on top of that. Okay. So essentially what you're doing is you're saying I bias it DC and I increment that DC value by a very small amount that it still looks linear, right? And then you get the response for that, which is almost linear. Okay, provided that this VD is still very small. Okay, so and remember, this is the key thing in small signal analysis, and people forget. So we did this calculations, right, for the uh, amplifier, and it turned out to be the gain was 40 because lambda was 0.1, which is a technology parameter, but the V effective was VDD2 minus VTN. That's because we biased it at VDD by 2. Now let's say somehow we want to bias it at VDD by 4. Now the gain is different because I have to go back and calculate the whole thing. Well, now we have a model. We can just substitute V effective with VDD by 4 and calculate it. But you can't tell gain is 40 anymore. So if the DC point varied sufficiently, especially much more than the signal variation itself, you have to go back and calculate these again, these parameters, because what you're calculating is this slope, right? But if you come here, this slope is completely different. Here, this slope is different. This slope is much higher. So if your DC point went from here to here, you have to go back and calculate this again. So that's the key point in small signal analysis. Just a notation. Unfortunately, I may not be following it all the time, but just bear with me and forgive me for that. But basically, this is at least for the books and literature. When they write it, typically they will write it this way. So when they have a small I and a uppercase subscript, it means it contains the whole thing. It contains both the DC as well the AC. That means the entire signal is there. And if you have uppercase um, signal name and subscript of uppercase, then that's only the DC part. You're removing all the variation part of it. And then the ID part of it, which is lowercase signal name, lowercase subscript, that's only the variation. And in small signal, that is all we are calculating about. So when I said delta V in over delta V out, I was calculating, basically I'm calculating small v in by small v out. Okay, so the DC bias, I'm just saying that's constant. I don't need to worry about it. The signal or the model doesn't perturb much, so that's why. Okay. So in other words, so graphical representation, like I said, and essentially what you're doing is you're taking a function and you're linearizing about a certain point, which is basically taking the slope at that point. Okay, so that's, or in other words, you're basically taking this curve and approximating it. And obviously, the higher the V in goes, the larger the error you'll get, right? So like I kept asking you, 1 millivolt, you said 40 millivolt. I said 40 millivolt, you said 100, 1,600. But once you go 1,600, your error is going. And obviously, you don't get to, 660 volt or 16 volt. You just clip, right? Your VDD. So, um, I mean, in gate, probably you have to write 160, otherwise they'll give you a 0, but in reality, that's not true. Okay, so this is another way of showing you. So like that question I asked you, or you asked me, like how much delta V in can I use till the model is valid? And my answer will be how much error can you tolerate? So like simple like diode equation, right? If you take a diode equation, which is ID equals to IS times e to the power VD over VT, right? So you can see I just took obviously just the exponential term because I'm looking at the error percentage. I don't care about the IS term. So if I do a Taylor expansion of the error term, I mean the exponential term, it's 1 plus Vm, or in this case will be Vd over Vt, and then square term, cube term, and I say I'm just neglecting it, right? So in this diode equation, if I take, actually there is 1 plus term, but just neglect that for now. Just we are talking about just the function. You can see as I take my input from 1 millivolt to 5 millivolts to 10 millivolts to 15 to 20, the error goes from 0.07 to 1.6% to 5.7 to 11.3 to 18%. And this is the error from the exact equation. So, uh, uh, so whatever is the real current versus the current you're going to calculate with the linearized equation, that's the error. Okay, so you can see for small one, 0.07%, even for audio, it's, for most audio, it's pretty fine. Now you get here, 18% for most audio is not fine, it'll be, but for other applications, it might be fine. Let's say you're doing data transmission, and in that data transmission, all you have is 4 levels of logic, that might be fine, right? You're still within your noise margin. So it all depends on the application. So there's not one answer like, okay, for what value is it valid? It really depends on the application, right? For high fidelity application, your error has to be really, really small. For low fidelity applications, the error can be huge. Okay. Okay, so just a little kind of a formal formalization of what we have talked so far, right? So essentially what you've done is this. So let's say we have a equation which is a nonlinear equation. So this is some nonlinear equation, right? So here I'm just writing IDVD because we just wrote equation for the diode. So I just, for sake of continuity, I'm just keeping that. But this could be whatever, right? Some input variable resulting in output variable, which is a nonlinear function of that input variable. Okay. So essentially what we are doing is we're saying this is a nonlinear function, and what we are doing is we're taking a Taylor expansion of this. Okay. And the Taylor expansion of this is the so I can break this down to a function which is the DC part of it and the small signal part of it. Okay. So, and if you do this Taylor expansion for this, you're going to get f of VD, right, plus the derivative of this function with respect to VD at VD. This is your DC operating point. In mathematical language at VD, but in circuit language at VD, right? Times the small signal. And then you're going to get the VD square plus VD cube term and so on. And you just basically kind of neglect them, right? So that's your, and this is your, in terms of your diode equation, that's, so basically what you're saying is that this equation for very small VD, you have the DC portion, and then you have the linearized, which is basically the linear term of your Taylor expansion, which is same as your slope. That's, so derivative actually means that, it's the first term of your Taylor expansion, and double derivative means the second term of your coefficient of your Taylor expansion. Okay, so for example, let's take the diode equation again. So ID is equal to some IS times E to the power VD over the thermal voltage, which is, this is obviously KT over Q, right? So I can, okay, I should write this as capital V, right? Which is equal to IS times E to the power the DC value, and then the small signal I'm giving on top of that, right, divided by VT. And then if you bring the VD out, because it's exponential, it's e to the power VD times e to the power small VD, right? So, and that is your, this current, right, your DC current, times e to the power small VD over VT, correct? Now, if I take the Taylor expansion of this, then this will be ID times 1 plus X, which is VD over VT, plus all the square term again over by 2 factorial, I think, VT square by 2 factorial and all that. I can neglect those. And then this becomes ID plus ID times VD over VT. Okay. So, and if I just take the small signal, so I'll say ID is equal to ID times VD over VT, right? So again, what I've done is I have taken the diode and done a small signal, small signal approximation or a linearization of it around the DC point ID. If the ID changes, then you have to go back and recalculate this bit. And what is this? This is just simply a resistor, right? Because if I take ID times R, so what is R? Let's call it what? R incremental is equal to what? VT over ID, right? And if you remember, this is also a small signal for something else. What is it? Transconductance of a BJT, right? VT over ID. So that's what you have done. You have taken a nonlinear element and linearized it to a linear resistor, right? Because it's a two-terminal device. That's why it becomes a resistor. Now, when we go to the MOS, now we'll see it's a four-terminal device. So now you have a four-port device, basically. Okay. All clear so far? So now you can, like taking that example before, you can apply AC. You have a 1K resistor. Now you apply that. Now you can do V out over V in by just doing this linear. So this is your R incremental of the diode. This is your R bias, right? And this is your small signal on top of it. Okay. So what's a small signal equivalent of a resistor? Just a plain resistor, like that 1K resistor. What's the small signal value equivalent of it? So yeah, so question is, see, the diode, I made an equivalent of it as the small signal module is a resistor. Exactly. So it's already a linear element. You don't have to linearize it. So small signal or incremental model for a resistor is a resistor. Same thing. What is the small signal equivalent of a capacitor? Same capacitor, because it's a linear element, right? So this is only for nonlinear elements, right? If it is a linear element, then it's the same. Okay, so when we do small signal models, we'll see that. Clear so far? Okay, so that's the demo I was talking about. Take a look. It's a very fun video. Um, so essentially what he's doing is he's gotten an entire like lab rack into the class, and on the oscilloscope it's showing how the DC slope is changing, and he has the audio amplifier which is blasting a music in the class, and it's all jarred, and he moves the point and compresses it and then amplifies after the diode and shows it. So it's a nice video. So take a look at it. Okay, so I don't think there is anything. Okay, so now we'll come to the MOS small signal part of it. So, when we did the amplifier, right? So what we did was, one second. So, so when we did the amplifier, we actually wrote the entire nonlinear equation for the amplifier and linearized it, right? But that's only 2 transistors. Typically, when you're doing analog, you have like 30, 40 transistors. There's no way on earth you're going to write an entire equation nonlinear and then try to linearize it. It'll go crazy. Even that analysis, actually, I did a lot of approximations. If you didn't do that, you'd be all lost, right? So just 2 transistors, you'll be all lost, right? That's because I kind of from experience, I know what are the things. But if you just gave you the thing, I said lambda p lambda and mu p, I mean, you'd be here for months, like trying to get the expression for it, right? So instead, what we do is we take all the nonlinear elements because they're the same everywhere. And when a nonlinear element is biased in one place and the linearized model is the same everywhere, if it is biased the same way. So in a circuit, let's say a transistor is biased to the same VGS, same VDS, same VBS in 5 different places. Well, the small signal model is not going to change. It'll be the same thing in the 5 different places too, right? So you find in one place, you can substitute in all places. So that's the methodology we're going to follow. Instead of writing the entire nonlinear equation and doing it, we'll actually find the small signal model for all the nonlinear elements. And then in the circuit, we'll replace them and then do the linear analysis. Okay. And so let me go through this, and then we'll go to the amplifier example and put these models there and see if we get this exact same answer. If you don't get it, then it's not good. Okay, so so MOS is a four-terminal device, right? So because diode is a 2-terminal device, we just applied a voltage, looked at the current, we linearized it to a resistor, right? Because now we have 4 terminals, so we can't linearize the entire thing at once. Or in other words, there are 3 input variables where the current is dependent on, right? VGS, VDS, and VBS, right? VBS is dependent through VT, right? The VT is varying through VT, and that's true. So your current is varying because of VGS, it's varying because of the VDS, it's varying because of VBS, right? So I have to now do partial differentials. So I have to hold 2 of them constant, vary one of them, find out what the incremental model is, then fix that, vary the other one incrementally, find out what that incremental element is, then fix those 2, vary the third one, and find out what the other one is. Okay. So because now you have a 4-port terminal. So that's what we're going to do that. So obviously you have 4 terminals. So this VBS, like I said, we're going to fix that. We'll call it VBS 0. We're going to fix the diode, the drain source also, which is, let's say, VDS 0. And then we're going to fix some VGS, which we'll call it VGS 0. So now it's biased, right? We have provided the DC bias. Now what we're going to do is we're going to apply a small signal just to the gate, keep everything else constant, right? So we're going to apply a small VGS, okay? And then see what is this current IDS, small IDS, okay? And that is called the transconductance. So transconductance is nothing but how is the drain source current varying with respect to variation in dVGS with VGS 0, VDS 0, VBS 0 bias. Because if I change any one of these, I have to go back and calculate this again, right? So that's your transconductance. And we'll do this for saturation, because when you are doing the gain calculations, it's always for either saturation or subthreshold. You know, rarely we have it for linear. But if you have it for linear, then you have to use the linear equation and get the models. Okay. So we'll do it for saturation. So what's the saturation current? ID is equal to mu C ox. I mean, I'm just keeping this agnostic to N or P, W over L, V effective square, right? VGS minus VT square. Okay. And because the VBS is not varying, that's fixed. And the VDS is not varying. I haven't included 1 plus lambda because it's not a big term here. So just to keep it, keep the derivations, you know, out of that derivation. So I'm just keeping the one which varies the most. So V effective square, right? So what I need to do now is I need to do DID over dVGS, right? For this equation here. And that will give me what? 2 times, actually this is mu and mu C ox over 2. So 2 times cancels. So mu C ox W over L V effective. And this is what's called your small signal transconductance. Okay. And you can also write it as, so this is what I can write V effective as, so this is equal to ID times V effective over V effective. So two ID. No, that's not, I'm looking at, uh, actually the other equation is 2ID mu C ox W over L root over, right? That's your GM also. So you can rework these equations and you'll see that, yeah, this is the other equation. So it's the same. Basically what you're doing is you're taking ID value and instead of V effective, you're substituting V effective, because I can take V effective over here, which is ID over mu C ox over 2W over L root over, right? From this equals to V effective. So if I take this, substitute it over here, you'll get this one. And similarly, you can write it as 2ID over V effective as well. Okay. You can do some algebraic manipulation and you can get this. So, and you know, in all the books, you'll find most text, you'll find these two equations, okay, which basically gives you GM as a function of W over L and, you know, mu C ox and all that, but those are properties. But that's because they don't design circuits. They actually solve problems given W over L. But the one which you'll be using in design is actually used. Actually, I can't remember when I last used these two things. And the last I used is actually at school when they gave me problems or when I'm giving you guys problems. But in design, you are always using this equation or most of the time. The reason for that is you don't know W over L. You're trying to find W over L, but you know your current budget and your voltage headroom budget. Okay. And based on that, you're trying to figure out what's the max GM you can get. And then you use the equation to find out W over L. Okay. So this is one of the equations you should always be remembering. Like as I said, that's why I kind of forgot this equation. But because I've, you know, frankly, I don't know when I've used it last. But all the textbooks you'll see, these are the equations they're giving you. But this is the one we'll be using. So when we start designing current mirrors and amplifiers, I'll show you how to use this equation to actually design. It's a very powerful methodology, which honestly, a lot of designers still don't do that. They actually use this equation, they go to the tools and they start playing around with a lot of W over L's and doing reverse. They shouldn't be doing that because the thing which is given to them is the power budget and the voltage headroom budget. So, and this equation beautifully captures that. So, and this equation also captures something which I'll come next to it. So this is one partial differential equation. So in MOS, like I said, you can't just have one small signal model like we had for this thing because we have three variables to it. So we found one variable, right? One which is called the transconductance. And the next one is I'm going to show you before I show the next two small signal variables, I want to just show you the small signal um, model transconductance when it is in subthreshold. Okay. Now, if you look at the literature for subthreshold, I actually don't find any consistent equation for it, but I think this is a good one which captures when you're designing it. So ID is equal to ID, some ID 0, that's your bias point, just like your diode, times e to the power uh, VGS over N times VGS over VT, where this N is typically equal to 1.5. So when you're in subthreshold, it actually looks like a BJT, but it's 50% worse than a BJT, which is still much better than a square law in the sense that current gain to voltage input, it's exponential, whereas in the saturation, it's a square law. So the amount of current change you get in the exponential way is still better, even the N is 1.5 compared to a BJT, okay? So this is kind of like I said, in literature, you'll find all sorts of equations. I haven't found a single consistent equation, but this is a good one for it, okay? So now if I want to find out the transconduction, that is basically, I want to find out the variation in ID for in VGS, then that is what? It's ID 0 times e to the power n VGS over VT times n by VT, right? And this is what? Your DC bias, right? So this is n times ID over VT. Where did we get this number right now? That was the diode small signal model too, right? Which is actually the same as BJT. So like I was saying, when we did the VT in the last lecture, so we say when the channel is formed, it starts conducting. No, it's actually conducting before that, but it's actually conducting like a BJT now. It's through diffusion. There is no drift because there is no channel charge, right? It's doing through drift. But that's fine. For low power ones, what I want is, I don't want a ton of current. I want the variation of current to be large with a small variation of VGS. If I get that, I can build high gain amplifiers with very low current if it is low frequency. If I want to operate it like gigahertz, then yes, I have to operate it in saturation because I have to pump tons of current, and that's when I need it to be operating in what do you call it? A saturation region, right? Inversion. Okay, so this is your GM. And a really good figure of merit or a term when you're doing analog design is GM over ID. This tells you how efficiently are you designing your transistors for an amplifier. Okay, so for example, here, if I take the ID here, what is GM over ID? N by? Sorry, I made a mistake here. Yeah, I knew I was something. So this is 1.5 times worse than a BJT. So means it has to be in the denominator. Okay. Yeah, because I was thinking, how come it's better than a BJT? Okay. So BJT is ID over VT. It's actually 1.5 times worse than VJT. So that's why the N factor N. But it varies from process to process. I'm saying typical values are 1.5. Okay. So this will be N by 1 over VT. So typically at room temperature, VT is what? 26 millivolts, right? 0.0, so let's say 25 millivolts. So what is this? 0.025 0.25 is 20,000 by 25 is 40 by 1.5 is what? Um, 26.666. Okay. And just remember this number. So when you start doing analog design, this number will be really, you'll be using this number a lot. Not 26.66, but trying to get to it. Okay. So this is like when your device is in deep subthreshold, your GM over ID is about 26.66. Okay. What do you think GM over ID is when you're in saturation? So this is when you're in subthreshold. What do you think it is in deep saturation, like heavy saturation? So for saturation, what do you think typically the GM over ID is? They're about 6 or 4. So if you divide this, so let's say it's 4, we go try to kind of make it dramatic. Same device, same current. If you go from, not same device, same current. If I take a device from saturation to subthreshold, the GM over ID improves by how many factors? 6 factor of 6, right? Typically, you don't get that. You don't get 6, but you can usually get 4 to the maximum. So what does that mean? What does it mean from a designer perspective? Like I was designing the amplifier. So we'll go back to that amplifier and we'll see, how to change the GM over ID. Less ID, more GM, right? So basically, I'm getting the same amount of GM with 4 times less current, which means that if I'm doing an amplifier, okay, and so it's usually GM times, so if you remember that equation we had, 2 over, what did I have? Lambda over VGS minus VT, right? Or we said VD, V effective. I can write this as 2ID times ID times lambda times V effective. What is this term here? We just derived it. It's GM. And this term 1 over this is actually R naught. That's called the output impedance. Okay. So what I want is a high output impedance if I want high gain and high GM as well, right? So high output impedance, like I said, you just change the lambda by changing the length. So you increase the length. In order to get GM higher, like I said, in your previous equation, we just had V effective, right? That was the only thing we could control. But that V effective, you can push it to the subthreshold and get more, juice out of that same amplifier. Yeah. So you're not going to get more gain. You're going to get gain of 40 because it's 1 over V effective. I can't go VD over 2, right? VD over 2. But we haven't calculated the current there. If you calculate the current for the saturation region, and then we calculated for the subthreshold region, you'll see that actually you could get more gain. This is only for saturation region. You could get more gain, but for that same gain, I'd be burning maybe 5 times or 6 times or 4 times at least less current. So for low power circuit, that's why it's critical. So you'll see when you're doing op-amp designs and you want to optimize it, your input pair of your op-amp should always be in deep subthreshold if you can afford it. What I mean by afford it is if you don't have speed issues of driving it or area issues, you always drive it into subthreshold. And that's something which still, boggles my mind is that a lot of designers, they'll just put it in threshold. So you're 4 times less efficient, which is huge. In low power circuits, that's huge. There's a legacy reason for it. So like 15 years ago, maybe, designers never designed anything in subthreshold region because the models were bad. So the models provided by the foundry, they're in the region of subthreshold, they were bad. So in the sense you simulated something, when the chip come back, it's totally off. Okay, so people were scared and and the saturation models were good, so people just used in saturation. But nowadays the models are really good, so you don't have to worry about that. Okay. I'll send you another paper, link to paper, and it actually gives you, so like I said, if you plot your GM over ID for different values. So we said what, 26. Let's say I have a table. Let me just. So yeah, so I'll send you a link to a paper where uh, it calculates what's called the inversion coefficient. It basically tells you if you have inverted the channel or not. And the correspondence of inversion channel to GM over ID is this. So 1.0. So this point tells you if it is inverted or not. So when your channel just inverts, your inversion coefficient is 1.0. Anything lower than that, the channel is not inverted. So for 22, it's about 0.5. For 28 is about 0.1. Then for 11, it's about 5. Like I said, I'll send you a link to a paper which has this equation. And 20 is this. And so when you are in basically anything above 20, I usually anything above 20, I consider it as deep subthreshold. Deep subthreshold. And anything kind of below 8 or 10, 8 is kind of moderate, but if you're in the 6th region, you're in deep saturation. And then here, obviously, you're somewhere in the middle. So you'll find out. So when we're doing current mirror, we'll see in current mirror, you want to be the opposite. You want to be in deep saturation. You never want to be in threshold because your matching is going to be bad. So, and this is how you find out. So when you're simulating, you just see your GM over IDs and you say, okay, I want the inputs to be heavily subthreshold, the current mirrors to be saturation, and that's how you bias it. But sometimes what will happen is, in order to go deep saturation, you'll see your device lens like become really, really huge. So you kind of say, okay, I'll just stay around 11, 12. That's good enough. Okay. All right. So output impedance. Say that again. How to bias it in subthreshold? Uh, yeah, good question. So you just increase your W over L. So for a given current, so let's say you biased a transistor with some current I, and you have some size, right? And it's some VGS. You have some VGS, and this is some W over L. And let's say this current is fixed. So let's say this was 10 microamp, and let's say this was 10 micron by 0.18, or let's say 10 by 2, right? Something like that. And then you find out the GM over ID is, let's say, 15. So I want to push it to 28. Then you just keep increasing the W. You can't increase W and L. Then the W over L will remain the same. You want to increase the W over L. Okay, so you keep increasing the W and it'll push it more towards it. If you decrease the W over L, then it'll push more towards this side. Or you can decrease the I, but here the argument is you keep the I constant, VGS constant, and how you do it. Okay, or you can decrease the VGS as well. But typically you'll see when you're biasing it, that's like a mirror or whatever it is, then your currents are given current based on your noise requirement or drive requirement or slew requirement. So you're just playing around with the sizes to drive it to subthreshold or saturation. Okay, makes sense? All right, so next we're going to look at the output impedance, and this one we're going to take the obviously again saturation, but so we'll have the V effective square times 1 plus lambda VDS. But now we're going to do the partial differential where we're going to do it versus VDS with everything else constant, right? VGS 0, also VDS 0, VBS 0. Okay. And if you do this, you'll see that this whole term, obviously the one term goes away. And um, yeah, so lambda times this term here, which is what? Your ID sat, right? that saturation, the DC bias point. Sometimes the people just write ID, or that's the difference. So it's lambda, and this is your output conductance. Okay, and if you want to find out the output impedance, that's 1 over lambda ID sat, which, like, I was showing you in this equation. So you remember we derived 2 times lambda ID, sorry, 2 times lambda V effective was your gain for the inverter, right? And this is equal to 2ID, like as I said, ID times ID lambda V effective. So you can see 2ID, this is your transconductance, and 1 over lambda ID is what? R naught. So when we do the small signal modeling, and maybe I'll give this you as exercise. So once I finish the small signal model, you can go back to that same problem, substitute the small signals, calculate the V out over VID, and you should get the same quantity. Okay, so that way at least it'll tell you that you don't mess up anything. So that's your what's called your output impedance, and then the substrate conductance is now. So okay, so just sort of, if I draw it diagrammatically, then this is what we did, right? So we fixed some value VGS 0, we fixed some value VVS 0, where typically it is 0 if source and bulk are shorted. Then we applied a small signal on the bias voltage VDS 0. Okay, and we are finding out what this ID is. So VDS over ID, that's your R naught, right? So that's what we calculated right now. VDS over IDS, let's say. So that's a small signal parameter we calculated. Okay, and same thing for the last one, which is if I again draw the circuit, we fix the VGS, but now we give a small signal on top of your bias of your substrate, and we fix the VDS as well. Okay. So ID equation is the same, but now we need to make VT as a function of VSB because we have been taking constant. So it'll be mu C ox over 2 W over L VGS minus VT as a function of VSB, right? Whole square 1 plus, but for this one again, you can just kind of neglect the 1 plus lambda. So then now you do a partial of ID over dVBS with all others constant, okay? And this, I'll just write the expression, should have it somewhere. So, and this will come from expanding you remember that VT equals to VT at VSB equals to 0 gamma times square root of 2 VSB plus 2 phi F plus phi F, right? So you use that expression here, you differentiate it, and this is called GMB, which is the body transfer function, and it actually hurts you. So if your source and bulk are not biased together, it will take away some gain because this is the negative term, okay? Actually, this is a positive term. The GM was a negative term. This is a positive term because your ID is going in the different direction. I'll show you when I draw the small signal. So this is equal to gamma times GM because that has the GM term in it, and 2 times the DC bias voltage of the source bulk plus 2 phi F. So that's this term here. Typically, when you're doing hand calculation, this is a small term, you can ignore it. And if your VSB equals to 0, then you can completely ignore it, okay? So that's your last term there, okay? So we had 3 variables. We found 3 partials for 3 variables, keeping everything else constant. So now that's your complete model for your transistor, okay? So let's build this low frequency small signal model. So low frequency in the sense we are not going to put any capacitance. So this is a DC kind of your signals are varying ever so slowly so that any capacitance in the devices, they're just looking as open, okay? So now if I take the 4 terminal device, so this is your bulk drain, source, and gate. And if I draw the equivalent small signal model for it now, so it'll have also these 4 terminals. Um, okay, so get to source, drain to source. So source, I keep it common. Let's say you can keep anything common, but it's easier to keep the source common. So this is, let's say, source. So your input, because we are ignoring the caps, so this is just a open, right? So your gate kind of just has this open. So output gate in impedance is infinite. So this is the source terminal, this is your gate terminal, and this is your small signal increment. Okay, this has no DC. The DC is gone now. Okay, you don't have any DC information right now because all your calculations were done with the DC parameters. So it's all captured inside the GM, GMB, RDS. If any of that changes where those parameters change, you have to go back and calculate it. Okay, so this is just open. And then let's see the first term. The first term is what? What is a change in the current from drain to source when your input gate source is varying by VGS, right? So let's say this is your drain node. Then this is a voltage control current source, right? And what is the scale factor? GM VGS. And I'm not showing the sign because I've shown the direction of this. Okay. All right. Now R naught. So R naught is between drain and source. So it's a resistance, right? So that's just a impedance because the current is flowing from the same terminal as you have applied the voltage. So it's just impedance, right? So that's R naught or RDS or whatever you want to call it, right? Different terms. So that's your RDS. And so what about the other one? What was the last one? GMB. So GMB is what? Drain to source current, but but it is in the reverse direction. So it's GMB VBS. I haven't shown the bulk, but let's say this is the bulk and you apply a small signal between bulk and source, then that bulk and source voltage will be in the opposite direction. So what it looks like is GM VGS minus GM VBS. And if your source actually has the input signal, then it's GM minus GMB. So it's kind of like I said, taking away your gain. So this is your small signal model now. So you basically take the 4-terminal nonlinear element, and this is your linear element right now. So when you're doing circuit analysis, you basically take your transistors and just plug this model into it, and that's it. You're done. Key things to remember, like I said, you set a DC bias, right? Right? And then you calculate all the small signal parameters and then create the model out of that. If this changes, then obviously you go back and change this, okay? Now, the direction of the current, what does it mean? The direction of the current, what does it mean? See, we have no DC. There's no concept of electrons and V over I anymore right now. That's actually thrown out of the picture right now because that's encapsulated within the the GMB parameter. So then what's the direction of the current? What does it mean to have a direction of the current? What do you think is the direction of the current? So you're in your inverter, right? In your inverter amplifier, if this was your sine wave, what was your output? Inverted, right? So that's why we got, well, in that equation, we kind of did this delta V where we took the magnitude, but if you keep the signs, then V out over V in, delta V out over V in should have been equal to minus GM R naught, okay? And that's, you can see from here, if I put delta VGS, I get a current which is flowing in this direction, which is in the reverse direction of this. So let's say, because, in that circuit, in the inverter circuit, those bulk and sources were shorted, right? Which means that there is no VBS, so you can actually take this off. So in most of the small signals, all you're doing is you're taking the GM and R naught, okay? And if you took the GM R naught and let's say the load was just a current source, then it's minus GM R naught. So all it's saying is that if your voltage is increasing, your output is actually decreasing. Or in other words, it's actually telling you the phase of the signal. So the phase is inverted. Okay, so GM phase in the same direction, GMB phase in the same direction as VGS or VBS, but the GM1 is inverted. Okay, so remember that in small signal, the current direction doesn't mean that it's some electrons flowing in that. It's actually because you're looking at change of current, right? So this VD is basically it's just showing the change of current. So all it means is that if I have a delta V increasing in one fashion, the output will be decreasing. If it is in phase, then I would show the current in this direction. Okay, so that's the important thing. And don't confuse this, because what will happen is if you have many transistors, you start putting it together, you have to kind of keep the signs consistent. Otherwise, what will happen is you'll come up with numbers which are wrong, or they'll cancel, or you'll basically get wrong numbers basically. Okay, so let me okay, forget the problem. Let's do that inverter one. So if I take this inverter, so for PMOS, okay, it's exactly the same model, because your change in delta VGS and change in IDS still remains the same. In other words, if I increase VGS, the IDS increases in one direction, right? If I increase VDS, the ID increases by 1 plus lambda times. So for change in current, the PMOS and NMOS doesn't look any different. They look exactly the same. Okay, so now we are going to look at how to take the circuit and actually make a small signal model for it. Okay, so we had VDD and ground, right? And so forget the resistance for now. We said the resistance is very high. No, that's the resistance you put in to bias the circuit. R naught is inherent inside the transistor. That's what you get because of the transistor function, because of that lambda, the early voltage. That's what you get. That resistor we put between the input and output, that we actually physically put a resistor to bias it so that it stays in the middle. Okay. So yeah, we have that resistor, but I'm going to ignore that in the small signal model now because I'm going to say it's very big. But let's keep it for now. Okay, so we have these two, and the source and bulk are sorted for both of them, right? Makes our life easier. So let's start. So this is V in, this is V out, right? Before you do the small signal, what you do is, so your first step is finding the DC operating point, right? That we did because we added this resistor. The DC operating point was VDD by 2. Then we do what? We calculate the small signal parameters. Small signal parameters, which is GM, R naught, and so on, right? And then you create the, actually then what you do is you make all DC sources independent sources. Independent sources 0. So if you have independent current source, you open it. If you have independent voltage source, you ground them, right? So DC operating point, we did this. Now calculate small signal. So let's say we assume we did that. We calculated GM, R naught, and all that. We did that. Now we're going to do is, so there is only one independent source, which is this source here, connected from here to ground. We're going to short it, which means that this node will become ground. Okay. And now we're going to create the small signal model for the entire amplifier. Okay. And all you do is you just take the transistor out, put the small signal model in. Take the transistor out, put the small signal model in. So initially when you start making model, you actually keep the topology same, put it, and then start making corrections, because you'll be inclined like, oh, this is in parallel, let me just short it, and then suddenly your models will be wrong. Once you have a lot of experience, you can start doing that. But right now, just replace them as it is. Okay. So let's start with this MN device here. So what is that? So from gate, which is VN, and the drain is ground, right? And the first element is GM, which is V out to the ground, right? This is the ground, and this is going to be GM times V in. So I should write this as V in. This is all small signal now. Okay. And then the next one is R out, which is between V out and ground, right? Correct? Everyone still here? GMB we can ignore because there is no VBS. VBS is 0. There is no variation in VBS. But the input is varying, the output is varying. That's why I need to have R0 and the GM. Okay, now come to the PMOS. Like as I said, PMOS looks exactly the same as PMOS. So which means that there will be a GM from V out to ground. And what should be the value here? If everything was same, if W, what did we take there? Mu N over mu P is equal to Wn over Wp. That means I can just write the same GM times V in here. And this goes to ground as well, right? And then what is left? The R out of the MP, which is from this ground to V out, R out, right? And both this GM, because the way they are biased, GM is equal to 2 ID over V effective, right? And R naught is 1 over lambda V effective, right? Now let's take this circuit and make it um, um, simplified. Simplified in the sense, this is ground, right? So I'm going to just redraw it. So this is V in, and this is your ground. So you have GM V in going from here to here. You have another GM V in going from the same point, V out to ground as well. So I don't have to do twice. I'll just do it what? 2 times GM V in, right? Same thing. I have a R naught going from V out to ground. I also have R naught going from this time, but that means there are 2 R naughts in parallel. So that means R naught by 2. Okay, so now just use your node equation. Well, there's only one node, and this is V out. What's V out over V in? Is equal to 2 GM times R naught over 2, right? Basically, I'm just taking this current and multiplying with the resistor because just one current source and transconductor and this thing. 2 cancels, so this is equal to minus GMR naught, which is equal to minus 2 ID V effective times sorry, I did a mistake here. No, what did I do? R naught is, yeah, sorry, 1 over lambda ID cancels. So the gain is equal to minus 2 over V effective times lambda. It's the same equation. We go from nonlinear. The only thing is the minus, like I said, I kind of messed up the minus because I just kept delta V out as a magnitude. That's why. But we already took the direction as the opposite. So I should have put the minus equation there, but you can fix that. So you see now how we simplified. Now we didn't have to write any nonlinear equation. We have a model, we know the values, we just plug it in, and it's just GM times R naught. Whereas we went through that whole circus to do all that VN to VN, Taylor expansion and all that, which is done here. But now you do the nonlinear element itself. Now every nonlinear element, you just keep plugging this, right? Which is basically your transistors right now. Okay. So I think we'll just stop here. Any questions?